next part of the Section 3 videos, we're going to look at the ideal gas law. Now here's where the ideal gas law comes into play. If you remember back into what we've done so far, we've talked about gases and their properties, temperature, pressure, all that stuff, assuming they're all constant, meaning they're either all the same temperature and pressure or they're both at STP. So what happens if, number one, the gases aren't the same temperature pressure, or number two, they're not both at STP, okay, a very specific temperature pressure. We have to find a way to relate those gases when those conditions aren't the same or at STP. So what we come up with is what's called the ideal gas law. And the ideal gas law was derived from the previous gas laws, Boyle's law, Charles' law, and so on. So we notice here we got pressure, we got volume, we got temperature, and we got N for moles. We have a new term here, R. R is referred to as the gas constant. This is a number that relates pressure, volume, temperature, and moles together when the gas is not at STP. Now, it's very important here as we're dealing with this. When we're dealing with R values, a couple things have to be set a certain way. Number one, the volume of the gases has to be in liters. Number two, temperature has to be in Kelvin. Number three, there are several R values. The only thing you need to make certain is that you pick an R value that matches the pressure unit. And it's that simple. So if you look on the bottom of page 384, there are 4 different R values that we're going to talk about. The first one is given the value of, just put these simply as numbered here. The first one, 0.0821, and it's assigned if the pressure units are in ATMs. Number 2, 62.4, if the pressure units are in millimeters. Number 3, we're not going to talk about that one because that's dealing with joules and energy, so don't worry about it. And number 4, 8.314, if the pressure units are in kPAs. Okay? So these are going to be the 4 that we talk about. And again, these are constants. You're going to be given these numbers. So how are these problems going to be set up? They're simply going to be set up just like we did with some of the calculations in section 2. You're going to be given pressure, volume, temperature, moles, mass, some combination. You're going to be given 3, and you're going to be asked to solve for the 4th one. Remember, volume's got to be in liters, temperature's got to be in Kelvin, and which R value you pick is purely dependent upon the pressure unit in the question or in the calculation. All right, now, so we're talking about R values and pressure units and conversions. I mentioned this a little bit ago. Remember, all these numbers are going to be given. These are constants. So whether we're talking about pressure unit conversions or R values, you just need to know how to use them correctly, okay? Because you don't have to look them up. All right, so the first thing we're going to look at here is we're going to look at a sample problem in the book, and then I'm actually going to have you do a different one on your own. So on page 385, there's sample problem I, and what it says in the question is they want us to find the pressure of a particular gas in atmospheres. They tell us the moles of the gas, the volume of the gas, the temperature of the gas. Since they want us to find the pressure in atmospheres, we're going to use a very specific R value, 0.0821. So what we're going to do is we're going to plug stuff into the ideal gas law. Pressures are X, volume we know, moles we know, temperature we know. We look up R, plug in the numbers, get our answer. It's that simple. Again, you got to make sure that you're keeping track of the units, and obviously you got to be able to do the algebra. Well, now let's just say the problem was set up slightly different. What if they said they want us to find the pressure in millimeters of mercury? How does that change the problem? It doesn't The only thing that does change in terms of the numbers we put into the calculation is the R value. The calculation's the same, but what we're going to do now is instead of putting in 0.0821, which represents the R value if they want atmospheres, now we're just going to plug in 62.4. Different R value, same type of calculation. Sure, we're going to get a slightly different answer, but we've changed units. Okay. So what I want you to do is work through this problem and obviously show me how how you did on this. The other two, just because we're kind of working through this, practice problems 1 and 2. Okay, on page 385 and right after sample problem I. Those are good ones too, just to make sure that you know what you're doing and we don't have any issues there. All right, next thing. Well, we've talked about PV equals nRT, and now we're back to moles a lot and things like that. Well, we can kind of add one more layer to this calculation if we think about what moles are and how that relates to a couple other things that we've done. We know mass equals moles times molar mass. We know moles equals mass divided by molar mass. Okay, we've been dealing with this stuff for a long time. Well, here's a connection we can make. If PV equals nRT and N is moles, okay, then instead of saying PV equals moles times RT, okay, we can say PV equals mass divided by molar mass times RT. So you see here, instead of saying N, we can now say mass divided by molar mass. And what we end up having is PV equals mass divided by molar mass times RT. Or, if you want to take it one step further here, you can see how PV equals mass divided by mass times RT divided by molar mass. They don't specifically show this as a calculation. Okay? It's just understood that you should be able to make that conversion from moles to mass and molar mass and be able to kind of adjust that equation if needed. Okay? So it's an important little curveball, so to speak, that we've got to be able to deal with. So what I've got here, these aren't ones in the book. These are just ones I want you to kind of work on. These are definitely ones I want you to show me so that I know you're on the right track. But what we have here is we're trying to solve for the mass of chlorine gas that we have. It has a certain volume, temperature, pressure in atmospheres. Therefore, we use 0.0821. Keep it nice and simple here. The molar mass of chlorine, just use 70.9. So what we want to do is find, well, what mass of chlorine gas would exist in that container. And you're starting out with PV equals nRT. Now we obviously got to adjust that. Here's another one. You can kind of work on both of these. Now they want you to find the molar mass of an unknown gas. You know its mass, you know its volume, you know its temperature, you know its pressure, and again, therefore we know its R value. So what you're going to do is you're going to take PV equals nRT, and again, we don't have moles here, as far as a calculation. What we're trying to do is find mass or molar mass. So what you're going to have to do is adjust that calculation. Okay? So I want you to work on these two, and at some point, in class, I want you to be able to show me how you got these answers. Last thing, just as a reminder, there's nothing new here. Okay? These are reminders. Okay? If we have gases that are at the same temperature pressure, this is nice and easy. All we care about is coefficients, because the coefficients give us volume ratios. It's B over A. Okay? Just like we did mole ratios. Number two, what if the gases are at STP? Well, then we can use molar volume. Okay? 22.4 liters for every mole. Now remember, these are good here. This is just like using mole ratios. This is just like using molar mass. Depending on the situation, depending on the conditions, you just adjust as to using the correct one. What if they're not at STP and what if they're not equal? Then you gotta just do a little bit longer calculation, depending on what they want you to find and what they want you to solve for. But if any calculation dealing with volume and moles of a gas, these are one of the three that you're going to have to use. Okay? The last video we're going to look at is just, again, kind of an extension of stoichiometry, kind of tying all the stoichiometry calculations that we've learned so far in this year.